So today we're going to explain the AS quiz for week 6. Now, what's weird is this quiz is mostly AP material, and there's barely any material on the organic. There's like 3-4 questions that are very easy. So I recommend you guys really go study organic, because I have a feeling she's gonna get the entire exam organic even if the quiz isn't organic or most of it isn't organic. Anyways, let's start. I'm gonna go like a bit fast because I've explained all of this before in the AP quiz, which I'm assuming you're gonna watch if you don't know the AP material. And like some questions are the exact same, and I explained them for like a long time there. Anyways, the first 6 ionization energies are 799, 2400, and then 3000, and then it jumps. What you're trying to do is you're gonna look where it jumps, like a huge jump from 3000 to 25,000. So it means your ionization energy, you draw a line, and the ionization energy is the one before it. So it is in group 1, 2, and it is in group 3. So in the AS, no, they call them group 1, 2, and then what we call group 3 in the AP, they call it group 13, 14, 15, 16, and so on till you reach 18. In the AS, they call them by groups 13. They don't call them group 3. Anyways, now the first ionization energy is the mole as a gas. Then you're going to take away an electron. So it's going to become a positive ion because it loses an electron also as a gas, plus 1 electron. And what's it called? And that's it. Moving on. And now this question is telling us about melting points. So basically just read the graph and answer. The strength of the metallic bond increases as the nuclear charge and number of valence electrons increases, which explains the higher melting point of beryllium. Beryllium has a high melting point, relatively. So it's because when your nuclear charge increases, your metallic bond increases, and it's also because Be2+. That's another reason why it's increased. Moving on. Nitrogen, oxygen, and fluorine exist as diatomic gaseous molecules. Memorize, it's obvious. And they have a low melting point because they have weak intermolecular forces. Since they have weak intermolecular forces, they're easy to break apart. They don't need a high melting point. Carbon exists as a giant molecular structure. Any group 4 atom exists as a giant molecular structure, and they are very strongly covalently bonded. So it is always group 4 is always gonna have the highest melting point. Moving on. Here you just need to draw. We know that N2 is a triple bond, or like it has a triple bond. So you're gonna have dot x, which is a triple bond. So this is 1 pair, 2 pair, 3 pair, and then each is gonna have its own loner pair. We already took this last year, if you can remember. It was chapter 8 or 9, I can't remember. Now here, lithium chloride. Lithium is plus, chloride is minus. So the X that was on this one's valence shell, it disappeared and it went to this one's valence shell, making it this. Now here you have Li. Why does it have 2 X's on it? Li is plus 1. So it only is supposed to have 1 X on its valence shell, not 2. And either way, even if it had 2, after it would give it to Cl, it's supposed to have none. It's supposed to be empty like this. And Li, they cannot be sharing. This is covalent. They're not covalent. They are ionic. Moving on. Now, pH4 is an exception we need to memorize because pH4 forms a dative bond. It's because pH4, they're gonna have 3 that are bonded normally and 1 H that's sharing 2 dots, both of which are P's lone pair. This is an exception. H is gonna take the lone pair of pH4 because it forms a dative bond, and the ones that form a dative bond are the exceptions because they're like a few species. I'd rather you memorize them. Let me write them down. So the ones that form a dative bond are NH4 plus, BF4 minus, H3O plus, PH4 plus, and Al2Cl3. These all form dative bonds, which means that the P will share a lone pair with the H. N here forms a lone pair with one H. P forms shares one lone pair with F. O shares one lone pair with the H. P shares one lone pair with the H. And Al, here this is the most confusing one. Later we're gonna have a question about it. I'll draw it out for you then. Now, the table below shows the values of the bond energies and the bond lengths of HCl, HI, and the third unknown molecule HX. Now, order them in reactivity. Now, the reactivity, you know the reactivity by the bond length. So it's the shorter the bond length, the more like force is between them, the stronger it's pulling in the bond. It's the stronger the bond is pulling in the two atoms. So it's the less the reactivity. So when you have a higher bond length, you have a higher reactivity. So HCl has the highest bond length, so it is the least reactive. Or wait. Yeah. Whereas HX has the second tallest bond length, so it is the second most reactive, and the bond length of 127 is the shortest, meaning they are the least. It's the most reactive. It's the easiest to break, and it also has the highest bond energy. You know. Moving on. Anyways, so here you have anytime it's between two atoms that are standing to each other, this is pi bonds. Anytime they react, like they're attracted to the nucleus or they're attracted horizontally, it's a sigma bond. Moving on. Okay, so which of the following molecules has 2 sigma and 2 pi bonds? Now we need to know something, that whenever you have one single bond, it's one single sigma bond. Whenever you have a double bond, it's 1 sigma, 1 pi bond. Whenever you have a triple bond, it's 1 sigma, 2 pi bonds. So now here you had a long list of molecules, and HCN is our correct answer. Why? Because HCN, when you draw it out, this is how it's drawn. So you have 1 sigma, 2 sigma, and 2 pi. So this is the 2 sigma bonds and 2 pi bonds. The single bond, we said already it's sigma, and we said that the triple bond has already one of these bonds is sigma and these 2 are pi. So this is why. Moving on. Okay, so how do you form a coordinate, aka dative bond? An atom with a filled orbital that is stable? No. You have an atom that has a lone pair of electrons and an atom that has an unfilled orbital to accept one lone pair. These are your only 2 requirements. Memorize it. Now, the ones with the coordinate bond, we said NH4 and Al2Cl3 out of these options. Because Al 1, 2, 3, Cl, Cl, Cl. And imagine I drew all the lone pairs, but I'm here gonna draw one, so I need to explain it. And then it's bonded to another AlCl3. Cl, Cl, Cl. And here you also have, let's say, another bond pair. This bond is gonna share with the aluminium because it needs an extra bond. And this is gonna share with this aluminium because it also needs an extra bond, or pair. It doesn't have any left to give. Moving on. And hydrogen chloride, the chlorine atom shares 1 pair of electrons with or from hydrogen to form a single covalent bond. We already know this, it's HCl, nothing new. Again, we took how to draw it last year. H can only form two, it can only give one and take one. It can't give more or take any, or it doesn't have any lone pairs. And it's not ionic, so this is wrong. Now, metallic bonding is the attraction between positive metal ions and delocalized electrons. I'm assuming everyone here took the IG, and we already know that it's between positive metal ions, or aka cation ions, and delocalized electrons. Moving on. Now, when a metal reacts with a non-metal, the metal loses electrons and becomes a positive ion because it has less electrons than protons. Whereas the non-metal, it takes the electrons, so now it has more electrons than protons, so it's a negative ion. And the strong force between the ions forms an ionic bond. Here you have ionic bonds are not drawn like this, they're drawn like this. And you have Ca2 plus, and F is F minus, because if it's F is in group 7, it can only take 1. Here it can give 2. So how will F, if it's, and Ca we know it's in group 2, so it's 2 plus. So this is immediately wrong. Here it can give 1 to each, because F can only take 1. Moving on. Electronegativity increases across a period and decreases down a group. It told you, but it's asking you why. It's because when we move across a period, the atomic radius, it decreases because the nuclear charge increases and they pull it in more strongly, so it decreases, of course. Now, as we move down a group, atomic radius increases. Yes, we know this because the number of, like the shielding effect, the number of nuclear, like the shells, increases, so it gets bigger. As we move down a group, the shielding effect increases. Is just literally just what I said. And as we move across a period, the nuclear charge increases. Yes, it does. But as we move down a group, the nuclear charge decreases. This is definitely wrong, because as you go down, you get more protons. So how would it decrease? Moving on. Okay, so what's the first ionization energy from left to right across period 3? We said when we go like this, it increases. This is the only one that's increasing, so it's the correct one. Now, next question. In general, ionization energy increases across a period and decreases down a group. This is because the nuclear charge increases, whereas the shielding effect and atomic radius, and the atomic radius decreases. We know this because they're pulled more strongly together. Shielding effect and atomic radius will increase down a group because you have more shells. Higher nuclear, like higher effective, higher N. Moving on. Why is it not flipping? Anyways, yeah. So what happens to the atomic radius down a group? Radii, my bad. They increase because it's more shells. You have more shielding. If you have more shielding, it's a way bigger circle, you know? That's why. And atomic radius, it decreases from left to right. Why? Because you have a higher nuclear charge. Since you have a higher nuclear charge, you have more protons pulling in the same number of, or not the same number of, but the same energy level of electrons. So it's gonna decrease. Now, going down a group, the ionic radius will increase. Why? Because you have extra shell, you have more shielding. So it's definitely, obviously gonna increase if you have more shielding. Positively charged ions are smaller than the original atoms, whereas negatively charged ions are larger. I explained this in the quiz, and either way, we already had a periodic in this. So I'm assuming everyone knows this from the periodic. Moving on. Okay, this is new. So what type of hybrid orbitals do you have in A? Now, first of all, when we look, you have to look. A is this bond, till this bond, so you cut. B is till this bond, so after this bond, or what it's connected to, you cut. C is in this bond, so you stop. You don't need to cut anymore. So let's look at section A. It's still here. What does it look like? It is a straight line. It's linear. Since it is linear, it's an SP. You don't just know linear means SP, and linear means the angle is 180. And you have 1 and 2 sigma bonds and 2 pi bonds. So you have both sigma and pi bonds because you have double or triple bonds. Now the type of hybrid in B, what's B? B is C at this is B. It's connected to a C here, H here, H here. What does this look like? This is a tetrahedron. Tetrahedron means there's 4. If it's a tetrahedral shape, it's sp3. Memorize these, by the way. Tetrahedral shape, sp3, and the angle is 109.5. You're gonna ask me, how do we find the angle? Don't ask me, I ask myself that. You memorize that. There's no way of knowing for us now. And look, here you only have 4 single bonds, so there's only sigma bonds. طالما you don't have any double or triple bonds, you can't have pi bonds. Now, for part C, this is part C. What does it look like? It looks like a triangle. If it forms a triangular plane, it is sp2 or sp2, and there's a bond or there's an angle of 120 between these. And since you have here a double bond, you have both sigma and both pi bonds. Moving on. Which of the following is a carboxylic acid of 5 carbons? Now the general formula of carboxylic acid is CnH2nO2. That's it. So if it's 5 carbons, here it's gonna be 5, here it's gonna be 2 times 5, which is 10 O2. That's how you get it. And if you remember also last year, it's it's like, this would be written as CH, wait, how was it written last year? CH something, COOH. Since you had, C4, and then you had H9, it's 2n minus 1, yeah. It was 2n minus 1, so it's CH9, COOH. That's how we wrote it last year, but this year we're following this type of formula. By the way, you should memorize these all from the book. I can't really explain them. You need to read the book. Here, how do you name them? So, first of all, when you see something like this, with practice, you could start naming it when you see it. But for now, I'd rather we draw it. So it's CH3, CH2, then CH, which means CH, and then this means it's a branch. So here you have a CH3. Then you have another CH. Then you have a double bond, CH. Then you have another CH3. Now, how do we name this? First of all, we're gonna look where's the functional group. Now, we're gonna find the position of it. It is on carbon number 2. It's after carbon number 2. So we know that we need to count from this way. We already know that when you name a branch, you need to find where the branch is the least, right? No. First of all, you need to find where the functional group is. And for the functional group, if you're starting to count from right to left, it means also for the branch, you need to count from right to left, even if left to right is shorter, or like a smaller number. So we identified that it's a C double bond C. So what's that a functional group of? C double bond C is a functional group of alkenes. So now we know it's an alkene, and we know that the position of the alkene is on carbon number 2, and here we have a branch. What's this branch? It's CH3. CH3 is a methyl. So it is a methyl. This is like a game, like you need to identify what can you find out about this structure. And what carbon is the methyl on? It's on carbon number 1, 2, 3, 4. So now we know everything we need to know. It is 4, then you put a dash. Then you write the branch, methyl. Then we need to count the longest chain of carbons. 1, 2, 3, 4, 5, 6. You have 6 carbons. So it's hexene. It's hexene. But since we have the functional group on 2, it's hex2ene. 4-methyl hex2ene. And that's it. Moving on. Here they're just telling you give the molecular formula, which means count. Literally means count. Count how many carbons do you have? We have 1, 2, 3, 4, 5, 6. C6. Count how many hydrogens you have. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So H12. Now count how many O's we have. We have 1, 2, 3, 4, 5, 6, O6, C6, H12, O6. This is our sugar, which is fructose. Now, what's the empirical formula? Empirical formula means give us the simplest form. So 6 can cancel with 6. They can all be divided by 6. So you'll be left with C. 12 divided by 6 is 2O. CH2O. Now, what functional groups do we have here? Look. So what groups do we have other than C and C bonded to H's and C bonded to C's single bonds? We have here a C double bond O, and we have an OH. OH is a hydroxide, or like a hydroxyl group. It's a hydroxyl group, and C double bonded O is a carbonyl. Carboxyl is C double bond C. Ester is C double bond O, and then so look, this is C double bond O. Hydroxyl is OH. Carboxyl, my bad, is C double bond C. Ester is C double bond OO. So what do we have here out of these options? We have these two. Moving on. Now, underline the functional group. I told you we have a C double bond C, which is a carboxyl. We have a carbonyl. We have a, here you have a carboxylic acid, and here you have an alcohol, the OH. Most of the times, just look for the odd thing out. Here you have all C's and H's and C's single bonded to C's. This stands out, this stands out, this stands out, this stands out. So it's very obvious. And this question, it was in the AP quiz, but I'm going to explain it really quick. It's methyl cations in a sea of delocalized electrons, because that's how you do metallic bonding. Is it a network? Covalent bonds, there's no metals that covalently bond to other metals. And is it a lattice of copper atoms? No, it's a lattice of copper positive ions. So 1 is the only correct one. Now, identify the coordinate bonds. Again, we had a question like this at the start. I explained this in my AP video, and memorize. Honestly, you can't really you can guess after you solve for a long time, but at the beginning it's just memorize. There's no really trick to it, you know? So just memorize the options I gave you at the start in the first question, and that's how you always know. Now, moving on. Down a group, electronegativity decreases. By the way, dative bonds, what I've seen, are most likely always between group 3. You usually always have group 3 involved. Or group 5. It's either group 3 or 5 involved. For dative bonds, you could be suspicious when you see anything from group 3 or 5. Just a trick that I've noticed from all of the dative bonds we have. Exception of H3O, by the way. That's our only exception that's not in group 5 or 3. So H3O plus isn't in group 5 or 3, and it's a dative bond. Moving on, again to our last question. So down a group, electronegativity decreases because your shielding effect increases. Across a period left to right, electronegativity increases because nuclear charge increases. And the Coulombic attractions between the nucleus and the electrons increase. These are definitions. They should be memorized. And that's it for this video. Hope you understood everything. Have a great day. Bye.